Hi, you're here with Tristan, Field Application Engineer at Nutaq. Welcome to this short video about MI125 crosstalk. MI125 is an analog to digital conversion card by Nutaq. It's a multi-channel card and it comes in two different configurations, 16 channels configuration and a 32 channels configuration where two cards are stacked together to make it 32 channels. The MI125 samples data at a rate of 125 megasamples per second, and the form factor of the card is FMC, which stands for FPGA mezzanine card. That means that the MI125 is actually a daughter card for an FPGA board. In this case, we're going to use the Perseus 601, which is the FPGA board by Nutaq based on the Xilinx Vertex 6 FPGA. We're going to be looking mainly at the crosstalk between the different channels on the same card. Crosstalk is oftenly used to characterize the quality of a multi-channel data acquisition card. So here I'm going to bring up MATLAB. After I install Nutaq's software tool suite, I get new demos from the MATLAB Help Demos menu. It's down at the bottom under Perseus 601. In this example, we're going to be looking at MI125 record demo. If I click on it, I get the demo sheet on the right-hand side. We have a block schematic showing what the signal path is going to be for this demo. So basically, we're going to acquire 16 different signals coming through each of the 16 channels of the MI125 card, and it's going to be recorded in the Perseus board's DDR3 RAM memory for a given period of time. After the recording is done, the data is going to be transferred from the board's memory to an external host computer via gigabit Ethernet. In the demo sheet, we have also step-by-step instructions on about how the demo is going to be run. So we're going to click on Open this model. That brings the Simulink workspace in which I will find a model made of blue blocks, which are Xilinx system generator blocks, as well as green blocks, which are blocks from the Nutaq's MBDK library. In this particular example, we're going to be looking at an array of 32 blocks. Each of them correspond to one channel of the MI125 card, and each of those channels are in this case rerouted to the SDRAM. Let me zoom in a bit here. To the SDRAM record block that's going to allow us to record the data in the Perseus DDR3 RAM memory. After the recording is completed, the SDRAM mem2host block as well as the RTDEX gigabit Ethernet blocks are going to be used to transfer the recorded data from the system to an external host using gigabit Ethernet, and that way we're going to be able to look at the data in MATLAB from an external host. As we have said, the MI125 is a daughter card for an FPGA board. So in this case, the Perseus 601 board with the Vertex 6 FPGA from Xilinx on it. In this case, the Simulink model serves to generate the FPGA bit stream that goes inside the Vertex 6 FPGA of the Perseus 601 board. And so I can do that by simply double-clicking on the system generator Redx here at the top left-hand corner of my model and click on Generate. For this example, this step was previously done, and the FPGA bitstream was downloaded via a JTAG interface into the FPGA of the. Once the FPGA bitstream has been downloaded into the system, I'm going to use Nutaq's command line interface to trigger the acquisition on the 16 channels of the MI125 card at a sampling rate of 125 megasamples per second. I'm using here the Nutaq's command line interface script that was supplied with the software installation, so the installation of the Nutaq's software tool suite. And in this script, I'm going to tell my system to do a burst of recording on the 16 channels for a given period of time and store the results in the board's RAM memory, and afterwards bring back the data onto the host, store it in a file that's going to be called in this case record.bin. And what I have done is I have previously ran the acquisition script, and basically I have hooked in a single generator that I use to generate a pure sine wave that I'm gonna inject into channel number 1 of the MI125 card. And the goal here, as we have previously said, is to measure the amount of crosstalk between the different channels on the MI125 card. Channel isolation or channel crosstalk is typically used to characterize the quality of such a multi-channel data acquisition card. And so the sine wave generated by sine wave generator here is gonna cover half of the full scale or the whole dynamic range of the MI125 channel number 1, which corresponds to minus 6 dBFS. What we will do, or what I have previously done in this example, is I have excited channel number 1, and obviously we're going to look at the crosstalk between channel number 1 and 2, 1 and 3, 1 and 4, 1 and 5, and so on. But doing it for a pure sine wave is good. But what we have done is I have made this exercise several times, and each time I have increased by 10 megahertz the frequency of that sine wave. So what that gives us is an idea of the isolation between channel 1 and 2, 1 and 3, 1 and 4, 1 and 5 for 10 megahertz sine wave, and then for a 20 megahertz sine wave, 30 megahertz sine wave, 40 megahertz sine wave, and so on. So here I will use MATLAB to plot the result or the data recorded in each of those individual files, which correspond to exciting channel number 1 with a 10 megahertz sine wave, and then exciting channel number 1 with a 20 megahertz sine wave, exciting channel number 1 with a 30 megahertz sine wave, until I reach 60 megahertz with an increment of 10 megahertz each time. And so here in this figure, what I do is I plot the crosstalk on the MI125 as a function of the nth neighbor, or how far two separate channels are from one another physically on the MI125 card. So on the vertical axis here, I plot the crosstalk in dBs. And on the horizontal axis, I plot the nth neighbor. So if we take the red curve, which is the results for the 10 megahertz sine wave injected into channel number 1 of the card, the result where the nth neighbor is equal to 1, so that's as a matter of fact the first neighbor. That would be the amount of crosstalk between channel number 1 and 2, where the second neighbor is the amount of crosstalk between channel number 1 and 3. The third neighbor is the amount of crosstalk between the channel number 1 and 4, until you get down to the 15th neighbor, which would show the amount of crosstalk between channel 1 and 16. And so for the 10 megahertz sine wave, we have a value here of approximately minus 68 dBs. So that means for a frequency of 10 megahertz, there's 68 dBs of crosstalk between the channel number 1 and 2. We see that as we go further apart between the channels, so if we look at the difference between channel 1 and 2, 1 and 3, 1 and 4, 1 and 5, we notice that the crosstalk decreases as the nth neighbor increases, or as we get further on the board. Here I have put an horizontal black line at minus 84 dB. The reason for this is that the MI125 card is a 14-bit card. And so if you multiply roughly 6 dBs times 14-bit, gives you 84 dBs, which is the dynamic range of the MI125 card. So if we look again at the 10 megahertz sine wave which was injected into channel number 1 of the MI125 card, and look at the crosstalk for the first neighbor, second neighbor, third neighbor, fourth neighbor, and fifth neighbor, we realize that after the fifth neighbor, the crosstalk disappears, so it's completely lost underneath the noise floor. On top of that, I have drawn a result for the 20 megahertz and 30 megahertz and 40 megahertz and 50 and 60 megahertz sine wave as well. And what we notice is that when we increase the frequency of the sine wave that was injected in channel number 1 of the MI125 card, the crosstalk increases. And so that shows that the isolation is better in lower frequencies, and that the crosstalk performance diminishes as the frequency increases. And so here, for the highest frequency at which we have run the test, which was 60 megahertz, the amount of crosstalk for the first neighbor was roughly 61 dBs, while as you get further on the board, the second neighbor, the third neighbor, fourth neighbor, down to the 15th neighbor, so between channel number 1 and channel number 16, basically the crosstalk at 60 megahertz will go down somewhere between 75 and 80 dBs. So that was Tristan with a quick demo on the channel isolation, or the crosstalk, on the MI125 analog to digital conversion card by Nutaq. Hope you enjoyed.